Take any positive integer. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. These two rules create a chain of numbers that bounce up and down, expanding and contracting with every odd or even turn. But follow those paths long enough, and they always behave the same way. Eventually, the volatility dies out, and every sequence crashes into a repeating loop of 4, 2, and 1. Mathematicians suspect this happens for every single integer in existence, but the arithmetic is so chaotic that no one has ever been able to prove it. For decades, the only way to test this was to pick a number and run the calculation. In the early days of computing, researchers checked every starting value they could reach. Every number fed into these mainframes eventually hit the 142 loop. But the number line is infinite, and computer hardware is not. You can check a quintillion numbers, but there's always a larger value untested. Tracing individual numbers through the arithmetic creates too much background noise. There is no way to see a global pattern one digit at a time. To find a definitive answer, mathematicians stopped treating the sequence as a series of calculations and started treating it as a shape. The first step in this shift is a mathematical mirror called the Bernstein-Lagarius conjugacy. It works by taking the sequence of even and odd moves a number makes and treating them as spatial coordinates. This process takes the branching, chaotic tree of arithmetic and wraps it into a single, smooth geometric surface. Because this mapping is an isometry, meaning it preserves the relative distance between points, we can stop calculating the values of numbers and start measuring the properties of the grid itself. The problem is no longer about whether a specific number reaches 1, it's about whether the flow of the entire system has a boundary. We can track that flow using a mechanism called the Lasota-Yorke inequality. This formula reveals a 2/3 contraction multiplier. As the system evolves over time, the total geometric volume it occupies shrinks by exactly 1/3. This contraction acts like mathematical gravity, pulling every possible path toward the center of the map. This forces the system down to an essential floor, a boundary that dictates how far any path can stray before being pulled back in. With a shrinking boundary and a solid floor, the system can no longer expand indefinitely. The possibility of a number escaping to infinity is gone. But even if we know the system is shrinking, we still need to prove that it doesn't get snagged on some complex interior obstacle. To verify this, the proof employs a Galerkin finite reduction. This process projects the infinite flowing operator onto a rigid finite grid. It allows us to calculate the exact frequency of the flow in manageable, modular cells without losing any structural detail. By pinning the continuous map to this grid, we can isolate exactly where the paths converge. Within this grid, there is still a potential for a number to enter a rogue loop, a cycle other than the 142 attractor. To find these loops, we look at the Arthur-Selberg trace formula, which compares the weight of the system's frequencies against its geometric paths. On one side of the scale, because the contraction is constant, spectral weight decays to 0, but the other side tracks cycles. A rogue loop would possess a constant, positive weight. This creates a direct contradiction. The shrinking vacuum can't support a permanent cycle. Since the math cannot balance, the rogue cycles themselves cannot exist. With the path to infinity closed and all other loops eradicated, every single integer is mathematically forced toward the 1421 attractor. This was achieved by ignoring the erratic behavior of individual numbers and instead measuring the overarching spectral frequencies of the system. By mapping the entire ocean of the number line, we finally understand why every single drop must eventually flow to the same place.